Onkar Dabeer. He is a faculty member in the School of Technology and Computer Science at TIFR. His research interest is mainly in multi-gigabit wireless communications and why you should be able to download a movie in minutes.
Or seconds.
Seconds is what he would prefer, but you know. So ultra high speed bandwidth communications is what he works on. Today he's going to tell us something much more common and what all of us use. It's about the mobile phone in your pocket. You've definitely heard about 2G and 3G, etc. Maybe in different contexts. But today we look at the scientific basis. What is 2G, 3G, etc. And before that, I don't care whether you have 2G or 3G in your pocket. Let's keep it bilkul chup hai ji.
Okay. Thanks a lot, Arnab, and thank you, Mr. Kulkarni, and the other core team for managing all the logistics, and thank you all for coming. So, as Arnab said, I mean, 2G, 3G has been much in news for the last 1 year. First, we had the 3G auctions last year, and there were crores, thousands of crores in that. Louder? Okay. And then, of course, more recently, we have had the scam. I mean, of course, there are all these aspects, but most people will agree that wireless communications has really changed our way of life, right? And in fact, like in the case of Dilbert, it seems that often our phones govern our life in some cases, right? So probably that's an extreme situation, not very good. But definitely it has changed our life. So when you take a phone and try to make a phone call, a lot of things are actually happening, okay? Your phone is first of all transmitting to the base station. Then from the base station, there are wires which will take it to some back station. There will be some processing there. Then the data, whatever you're sending, all that information gets into the core network, and then maybe it is routed to a different city or so. So these 2G, 3G, 4G, these technologies are actually with respect to the first hop. So this is these technologies tell a cell phone how it should speak with the base station, and they tell the base station how they should speak with the mobile phones, okay? So that's what I'm going to talk about today. The idea is to try and introduce you to some of the technology underlying there and what are the basic concepts there. So that's what I'll focus on. It looks like the audience here is very diverse. So people probably have very different backgrounds. So if you want, don't wait till the end. If you have a question, just raise your hand and stop me at any point, okay? That's totally fine. So, okay, so let's get started. So if you want to find about, we are of course in the information age, right? And so if you want to find out about anything, you just go to Google or Bing and you search, okay? Maybe you go to Wikipedia. And if you go to Wikipedia and let's say search for 4G, you will start gleaning a lot of information. So 2G was really technologies which in the Western world were introduced around the mid-90s, okay? They were the essential idea was to let people talk to each other over mobile phones, okay? Right now we do a lot of browsing, but then that wasn't really something that was in the mind of people, okay? And if you look at, of course, people slowly adapted these systems and they also started sending email over these systems. And typically they would support slow speeds, about 100 kilobytes per second. So just to give you a comparison, that's maybe double your dial-up modem, okay? Then came 3G. The standards for 3G were sort of ready around 2000, but it took time for these things to come into market for various reasons. In the Western world, this technology is sort of commonly used for the last 5-6 years. In India, it's only starting to roll out now, okay? And then there's of course 4G, which promises even more. So from each generation to the next, we are sort of going, there is a 10-fold increase in the data rates, okay? But when you go from 3G to 4G, something else is also going to happen. While these original networks, they always had voice as an important part, now we are essentially saying, look, virtually everything is data. And so we are not going to design our network specifically for voice. We are just going to treat voice also as data. And we are just going to use the VoIP technology, the same sort of technologies that you use when you're doing Skype, for example, right? So this is a major paradigm shift. And now most of the traffic is going to go towards data and video, okay? That's where we are headed to. 4G is starting to roll out in the Western world, particularly in the US. In India, it might still be a few years before we see it, okay? So if you really want facts and figures like these, I don't think I can do much better than Wiki, okay? So I think a good purpose for this Chandwa is to try and go beyond this, okay? Beyond what you can actually learn from a few Google searches and Wiki. And that's what I'm going to try and do. I'm going to try and tell you about some of the basic concepts, okay? Now, most of you are aware of mobile phones, maybe most of you use mobile phones. And so at some point or the other, you may have learned a lot of buzzwords, right? So maybe a few years back when you were trying to buy a phone, the first question that used to come to mind, should I buy a GSM phone or should I buy a CDMA phone? Okay, so what is this GSM? What is the CDMA, right? Now people want to read emails. Some people want to connect to Facebook, right? So if you want to do that, people will start wondering, oh, should I buy a GPRS phone or should I wait for 3G? Should I just buy a 3G connection? Then there are, if you're slightly more enthusiastic about technology and go and read blogs, you'll see that, oh, there's something called as LTE, long-term evolution, that's coming up, and it uses a technology called OFDMA. Okay, so I'll try. What my effort is going to try and tell you about all these things. And of course, spectrum and scam has been much in news. Unfortunately, scams are not my expertise, so I won't be speaking much about it. Okay, but spectrum is a very central concept, and in fact, to understand all these other things, to an extent, you need to understand what the spectrum is. Okay, so I'm going to do that. I'm going to start by telling you about the spectrum. So what do we know? Well, one thing we clearly all know about spectrum is it's something very expensive, and a lot of money is being put into it. Okay. Clearly, there was the scam. If you just look at the figures for a spectrum in Delhi, for example, Vodafone paid about 3,000 crores in the auction last year, right? The finance ministry has actually realized that there is a lot of money, and in fact, they are actually encouraging DOT to auction more spectrum so that they can actually control their deficits. Okay, so it's really big money. But what is this spectrum? So it turns out that this is actually, in a way, a very abstract concept. Okay, but now it has become so common in engineering that actually it's almost like real estate now, okay, at least for these operators. So to understand it, you actually need to go back to your high school. So I see that there are some people who haven't been to high school, okay. So but I'll try to explain it for them as well. So there is something called as a sine and cosine functions, right? So those who have done high school probably know it, and let me just remind you, these are periodic functions in the sense, okay, so let's look at this function. This is just a wave that goes in, and then once it reaches this point, it sort of repeats itself, right? And then there's this cosine wave, which is really the same as this, but it's just, let's say, shifted a little bit to the left, right? So these sinusoids are special, and you encounter them in trigonometry, right? There you look at triangles, and you define it in terms of the opposite side divided by the diagonal and things like that, right? But they have a life way beyond trigonometry, okay? And they are actually functions which occupy sort of the center of, one of the few functions which occupy the center of mathematics. So the first property of these things, as I said, is they are periodic, right? So they repeat themselves. Now, any periodic phenomena, right? It's going to occur, the same thing is going to be seen again and again and again, right? So the frequency at which this is happening is called as frequency, okay? So for example, in this picture, I've shown the time scale goes from 0 to 1 second, but in this 1 second, I have seen 2 cycles, right? So we will say that this is a sinusoid with frequency 2 hertz, okay? That's the basic idea. So whenever you hear, so even if you're listening to FM radio, right, you tune into a frequency, say 93.4, right? So that's actually a frequency, and that refers to how many cycles you're seeing per second, okay? So, but what's so special about these, right? I mean, there are a lot of, like I can draw a lot of periodic curves, right? What is so special? So they are special in a certain sense that if you take arbitrary signals, we can represent it. So what do I mean by a signal? Well, let's look at our cell phone. How do we communicate? Well, I'm speaking something, then there is some circuitry which actually, what I'm speaking induces some voltage fluctuations in that circuitry, okay? Then you do some processing on these voltage fluctuations and create some other voltage fluctuations. Then you, through the antenna, send them as basically electromagnetic waves over your medium. Then there's a base station. It has an antenna. These electromagnetic waves that you sent, they induce some fluctuations there. And again, there is a new voltage signal that is created there. So think of, whenever I talk of signal, think of these voltage fluctuations happening in your circuits, right? Because they are the ones which are actually carrying our messages. Now, what Fourier, who was a mathematician, what he saw was that give me arbitrary signal, waveforms, and I can express them as combinations of sinusoidal waves. Okay, so that's very interesting, right? because now I have these sinusoids, there is this class, I can just tell you what is the frequency, and I have many such sinusoids. But what he's saying is you take different ones, you mix them up in different proportions, and you're going to get all kinds of signals. And this is a very strong property in the sense that you give me a signal, I can actually split it into various sinusoids, right? So this is a very nice representation to have. So what do I mean by this? Let's take an example. Okay? So here in this picture, look at this red curve, right? Now how could I describe this signal? I could say, look, this signal, anytime you're between minus 0.25 and 0.25, this signal has value 1. Otherwise, the value is minus 1, okay? So suppose we want to represent this signal, right? So it turns out you can do the following. First of all, you take a cosine with amplitude 1. Then you take a cosine with amplitude minus 1/3. So remember the phase is shifted and the amplitude here is like 0.33. That's minus 1/3. Okay, and then you take a cosine with frequency 5. So there are 5 cycles here in unit time, and its amplitude is 1/5. Okay. If I add these, what I get is curve like this. As you can see, I'm coming pretty close to this, right? So it's an approximation. But what Fourier says is that you can go further. You could take, for example, a cosine wave with 7 cycles, okay? Then you could take 9 cycles, choose their appropriate weights, and what's going to happen is, eventually you will be able to come to this signal as close as you wish, okay? So this now gives us a different way of thinking, right? Given a signal, I could just think of it as voltage fluctuations, and I can tell you, look, at this time the value is this. That's one description of the signal. But there is now another description that Fourier is telling you. Fourier is telling you, no, instead what you should tell me is, this signal has frequency 1 as a component and its amplitude is 1. It has frequency 3 as a component and its amplitude is minus 1/3, right? And so on. So this is now a different description of the same signal, okay? So is this clear? Any questions here? So remember, this is an abstract notion. We are starting with these sinusoids, which are periodic waves, and we are saying that arbitrary voltage fluctuations can be actually described in terms of these sinusoids of different frequencies. All right. So, I mean, clearly, right, this is already a very abstract concept, but now over the years, engineers, everybody has got so used to thinking about signals in terms of their frequency components that signals are actually completely described that way, okay? So for example, let's look at a typical spectrum occupancy, right? So by spectrum, what I mean is really just the collection of these frequencies, okay? So that is what a spectrum is. So it comes from this abstract notion of representing signals, but it has now really ingrained into the minds of the engineers and the people who deal with these technologies. So let's look at the following things. I'll tell you about a technology, and I'll tell you the typical band it operates in, and then there is this notion of bandwidth, okay? So FM radio, right? So you take FM radio, typically goes from 88 megahertz to 108 megahertz, right? And then you tune onto a specific station in between that will be like 93.4, okay? Something like that, right? So what is happening here? This is now a band, and all your FM radios signals, they are more or less concentrated in this band. So what it means is that if you take your FM signal, which is nothing but just the voltage fluctuations on your FM radio, and if you look at their description in the Fourier domain, which is in the spectrum domain, and you ask which frequency components are occurring there, you'll see components only in this range, okay? 88 to 100. Even amongst that, I have different stations, right? So if I pick 93.4, what you'll find is that effectively that station, the signals will be centered around the frequency 93.4, and there will be deviation. It will occupy some region around it, which will be about a length of 150 kilohertz. Okay. Okay. So we have to somehow, because this is the same medium, right? We have to share this medium. We have to share it across different technologies. And the way people think about the spectrum is the way by which we allocate resources. Your signals should occupy only this portion of the spectrum. Your signal should occupy only this portion of the spectrum. That way you don't interfere with each other, okay? But remember, what I told you is just an idealization. In reality, it's never going to be possible for you to strictly restrict anything to that same frequency. So there is always going to be some leakage outside that, okay? But there are norms. So just like we have manners and etiquettes, there are detailed norms that are given by various standardization bodies, and they'll tell you, look, if you are so much away from the frequency that you were told, you cannot have more power than this, okay? And these are norms that everybody has to follow. And of course, for example, now if you take GPS, then the civilian signal that we use, that's centered around 1.22 gigahertz and occupies about 1 megahertz, okay? And so you can keep on going that way. There is GSM, 3G, Wi-Fi, for example. Most popular, there are these two options, right? 2.4 gigahertz and 5 gigahertz. And typically it will occupy about 20 megahertz. And then there's 4G coming, okay? So, but the bottom line is that there is this given a signal, which for us, for a person who's trying to communicate, there are these voltage fluctuations in your circuitry which are carrying your message. An alternative way to think about them is to think about the frequency components that are occurring in these signals, okay? And now it's so much ingrained in our mind that we actually use this abstract concept to say, to basically divide different operators, to divide different technologies so that they don't interfere with each other, okay? So that's the, yeah. So let's actually go to your 2D geometry, okay? Let's say we have two users, and let's say there is a game between them, okay? They both want to communicate. So here is a vector, and there is another vector orthogonal to it, okay? So what user 1 does it, if he wants to send a message, he picks a point on this line. So let's say he picks up the red point, okay? What user 2 does is if he wants to communicate something, he actually uses the blue point, okay? But of course, they are sharing the same 2D space, right? So somebody who's trying to listen to them, he doesn't get to see these points individually, but what he gets to see is actually this purple. I mean, the colors here are not visible, but this is supposed to be purple. So it's actually a superposition of blue and red, which ends up giving you a purple color, okay? So now at the receiver, right, from this purple dot, if you're only interested in user 1, you have to figure out what the amplitude was, because that's where all the information is hiding, right? So how would you do it? Any guesses here? Sorry? Okay, but something even more simple in this diagram. So suppose you knew that you knew the direction in which the person is sending, but you don't know the amplitude. Then one thing you would do is you'll say, okay, this point, let me project it onto this direction, right? That's a very simple thing you can do, right? And then what has happened is suddenly, by doing this projection, all the interference that was there from that guy has vanished, but you can actually figure out what this point is, and you have got your message, right? So what did we use in this picture? We use basic geometry, right? First of all, we have is this notion of length, because amplitude is really how far away I am from the origin. So there is a notion of length, but there is more. There is a notion of angle, right? If, for example, this axis was not orthogonal, then if I took the projection, there will be some residual left from there. The projection won't be perfect, right? So there is a notion of orthogonality, so there is a notion of angle, okay? It turns out that actually all the signals that we have been talking about, all these voltage fluctuations in your circuitry, they also have a certain geometry, okay? So you can define a geometry for them, you can define a notion of length for them, you can, given two signals, talk about the angle between them, right? And you can do precisely what we did here. You can assign one waveform to one user, one waveform to another user. The messages will be encoded in the amplitude of these signals, okay? But if you know roughly the shape of the signal, then you can project onto it and get the answer that you want, okay? So it's the same geometrical principle as this picture, okay? It's just that now we are going to apply this geometry to signals rather than applying it to these coordinate points, okay? All right, so now given this basic idea, right? So we want to now generate signals which are orthogonal, but there is no unique way. There are a variety of ways, right? For example, even in 2D, I could have a basis which looks this way, but I could rotate it, and that still gives me an orthogonal, right? These are three, and I can make any choice, right? So similarly for signals, there is no unique choice, and there are a variety of choices you can do, okay? So people over the time has actually come up with a few ideas. So here is one of the common ideas, okay? So this is TDMA, and this is what is commonly used in your GSM, okay? So what you do is, okay, this is the spectrum, this is the frequency band that's allowed to me, and this is my time axis. What I will insist is that during this time, user 1, or rather the blue user, gets all the spectrum, then during this time, the red user gets all the spectrum, then again the blue, then again the red, okay. So sort of you're saying, okay, each guy only operates in certain prescribed times, okay. So that's why, so there is good manners and you're not colliding with each other, okay. That's one way of doing it. Well, you might have heard of CDMA, right? So Reliance Networks were CDMA. So what is CDMA? Well, CDMA is different. It doesn't do any such division in time and frequency. Both the guys are allowed to be on at the same time, and they're also allowed to use all the frequencies at the same time. But the picture is more like what I showed you on the previous slide, okay? Those signals that I showed you, actually they turn out to be orthogonal. So you can create signals which are occupying all the time, they're occupying all the frequency, but they are nevertheless orthogonal to each other, okay? So that's what they do. So if you just look at the time frequency plane, then these blue and red, they are just superimposing and you're getting this purple, okay? But they are on, both of them are occupying the entire time. Now, if you're reading technology blogs, you might have heard of OFDMA, okay? So this is for orthogonal frequency division multiple access. So this is what is fourth generation telephony is going to be about. It's also related to, as one of the persons was pointing out, to what is actually done in the recent Wi-Fi standards, okay? And what it does is, it goes one step further. It says, no, look, what I'm going to do is I'm going to divide my time and frequency resources into small tiles, okay? And then I will decide how to split this. So for example, during this initial time period, the blue user gets this frequency block and this block, and the rest is given to the red. But when I go to the different block, then there are changes, okay? So there are these variety of options, and the way to think about these options is simply these are coordinate axes, okay? You could decide to write your points in 2D plane using this axis, or you could rotate it and decide to write it using these, okay? So it's really a choice. Similarly, this is a choice. So there are a variety of options, right? But for technology reasons, people want to make specific choices of these options. So what are these specific choices? So GSM. So GSM made the choice of using FDMA and TDMA. So let's say you have a GSM operator, you have been given a certain chunk of spectrum to operate in. What's going to happen is you're going to split this block that was given to you into 200 kilohertz bands, and then on each of these 200 kilohertz band, you're going to do TDMA. So you're going to tell, the base station is actually going to tell mobiles, okay, you communicate at this time, you communicate at this time, you communicate at this time, and everybody has to follow that etiquette, okay? So this is GSM. Now, one of the things that the early days when GSM was designed that it didn't do very well was, even though actually it established this etiquette, this is the etiquette followed with respect to a certain base station. But what if I have different stations and there is somebody in between who can listen to both the base stations, okay? So doing this, actually these guys can interfere with each other and they can actually disrupt each other's calls. So that part of the design was a little lacking, and so you could not use all the frequencies everywhere. And that gave opening for a technology called as CDMA. And CDMA stands for code division multiple access, but a code is nothing but a signal, okay? So whenever I'm saying a signal, instead you should, it's just the nomenclature that is used by the engineers. They call it a code, okay? So what these guys did was they allowed the signals of different users to occupy the same time and the same spectrum, right? But they were still orthogonal. And with that, they were able to use the spectrum better. Of course, the GSM guys soon figured out what the problem was with their design, and they slightly tweaked their design so that they could also get that advantage, okay? So if you look at third generation CDMA, which is now starting to roll out in India, the choice it makes is it divides users by codes, but each code corresponds to a group of users, and then amongst these group of users there will again be a time sharing, so that will be TDMA, okay? So it's a combination. And 4G is going for this last picture that I showed you, where there are these small time frequency tiles and basically you're communicating using, so that's the coordinate system, so that's the orthogonal signals that they use. And the main reason for that is, look, nothing is ideal in this world. So you might be sending stuff which is orthogonal, but it goes through this medium. There are all kinds of reflections, you go through all kinds of buildings, and what you receive at the end is nowhere as clean as what you had sent. So you have to correct for these distortions in order to actually figure out what was sent, okay? It so turns out that the kind of distortions you see in these wireless medium, you'll be able to handle them much more easily computationally using OFDMA. So actually the preferred way. In the past, it's not something that OFDMA was not really discovered very recently. It's actually from the 70s. But the reason people did not use it then was that there are some issues associated with your power amplifier, okay? And then the RF technology wasn't so good, but by now we have figured those out, and so OFDMA is back. That's now becoming the de facto standard in most of the modern systems. So you take your DVB standards for your dish antennas, you take your Wi-Fi, you take 4G, you're going to find OFDMA in it. So okay, so just recap. So I told you about spectrum. Spectrum is really an abstract concept that came from Fourier representation of signals, okay? But now we use spectrum to divide resources of the medium between different operators, between different technologies. When you go for a look at a single operator, the spectrum itself is divided in a variety of ways, and there are these various choices, PDMA, CDMA, so on and so forth. So are these the changes? So remember in the first slide I showed you that from 2G to 3G and from 3G to 4G, there is almost a 10-fold increase in average data rates from an individual's point of view. So are these multiple access technologies the reason behind it for this 10-fold increase? Well, the answer is no. Yes, they do make processing easier, and you do squeeze out certain bits from that extra, but they're not going to change the paradigm completely. Maybe they'll give you 10%, 20% increase, okay? So where is this 10-fold, 100% increase actually coming from? Well, one thing, people are starting to use bigger and bigger spectrum, okay? The other thing is multiple antennas. So if you just take your Wi-Fi router, you'll see that these days they seem to have horns sticking out of them, okay? In fact, if you walk down corridors in offices, you'll find at various points there are these, and they might actually have 4 and sometimes even 8 horns, okay? So these are multiple antennas. So the buzzword is MIMO, which stands for multi-input, multi-output. And the basic idea is that you want to use multiple antennas. So what does this MIMO do for you? So the thing that everybody who's used a mobile phone is familiar with is dropped calls, right? So why are these dropped calls occurring? So the basic idea is, from your high school you might remember constructive interference and destructive interference, right? I have two waves, and depending upon the phase in which they add, the amplitude might actually decrease, or they might actually end up cancelling each other, okay? So actually exactly the same thing. So for example, example of that is resonance, right? I mean, you might have heard of stories about soldiers marching on a bridge, and somehow the natural frequencies of the bridge were matched with these guys, and the bridge ended up collapsing, right? So that's where these waves are actually adding constructively, right? The other example of destructive is if you can buy these fancy Bose headphones, right? And what they are going to do is they are going to do active cancellation. They are going to actually try and look at the ambient noise around you, and they are going to create signals which, as far as possible, are opposite in phase to them, so that you can actually end up cancelling those signals, right? But this is something not under our control in wireless communications, because you're walking, probably you're not even in the direct line of sight of a base station. All the signal that you're getting is actually coming through reflections. These reflections could be anything. You might be on a street, there might be cars passing by, which are really metal objects passing by. Each car is giving you different. So there are all these phase changes happening, all these different reflections, and there is no way for us to control whether they are adding constructively or destructively. And that's the reason, actually, if you look at a typical signal, you will see a lot of fluctuations, okay? And by fluctuations, I mean not necessarily these, because these are inherently from your sinusoid, but look at the amplitude, right? That amplitude itself is actually, right? So here I got destructive interference, but here I got constructive interference. So how do you deal with these things, right? Well, one idea is you don't put one antenna, you put two antennas, okay? So what happens? So imagine as if there were two reflections. If you had only one antenna, what you're seeing is you're seeing a mixture of these two signals, right? And you don't have control over the phases, so you just have to live with whatever, this is what is called as fading. You have to just live with whatever fading is there, right? But now you put two antennas, right? What happens? Now you're not seeing one mixture, you're seeing two mixtures of two signals, right? And if these were sufficiently far apart, you expect these mixtures to be different, right? Now how does this, why does this help us? Well, just think of it this way, right? If I had just had two unknowns, let's say x and y, and I told you x plus y is 10, and I ask you, tell me about x and y, there is no unique answer, right? You can split it in any way. But suppose somebody came and gave you another equation. They told you, look, x minus y is equal to 4. Well, you know the answer. Well, it has to be, you can just add, right, 7, 3. He already has the answer, right? So the answer is 7, 3. So the situation is similar here. Now you have two paths, but now you have two antennas, so you have two sets of observations. So in this equations example I gave you, I had two unknowns and I had two equations, right? And that enabled me to solve the equations and get the correct answer as 7. So there is hope that if I put 2 antennas, maybe I might be able to actually resolve these signals. And if I can resolve them, then maybe I can shift them around and add them in a way so that they actually add up constructively, right? So there is hope for that, right? Now in real world, of course, this cannot be done ideally because all these things are changing, but it turns out that the idea actually has merit, and this is what is commonly used in 3G. So in 3G itself, there were multiple antennas, but they were primarily used for this purpose, which is to reduce the fluctuations in the net signal that you're seeing. And just to give you an example, if you put 2 antennas, and let's say you are communicating with a certain power, and then to get the same error rate that you were seeing earlier, with 2 antenna properly placed, you might be able to actually able to transmit only at half the power. Okay, so that's substantial savings, right? And the reason that is happening is because these fluctuations are actually reducing. Okay, but when you go to 4G, there is something even we can use these multiple antennas for a different rate. And here, let me take a slight detour into something called as information theory. So probably one of the most brilliant men of the last century, Claude Shannon. Okay, Claude Shannon was a mathematician who spent a lot of time at Bell Labs. But he wasn't just a mathematician, he was actually a tinkerer. Okay, he used to build his own toys, build mice which could actually run through the maze and find their cheese. Okay, and as is often the case when you have a mathematician who's also a tinkerer, they can actually think of good abstractions for real world problems, right? And that's what he did. He gave a framework called as information theory. Okay, and there are a few fundamental results in information theory which have driven the communication system design, okay, since the mid 40s. So his landmark paper came in 1948 and 49, and even now if you take any communication system and you look at the basic block diagram, it actually has that. Okay. So what did Shannon say? Well, Shannon gave a mathematical way about thinking about communication, and what he told you, what he came up with was that there are fundamental limits. So if you want to compress a signal, there is a fundamental limit. You cannot compress it beyond that. Okay? And he told you how to compute that. In our context, what do we want to do? Well, I have some information. Maybe I have a file that I want to send it somewhere. It consists of bits, right? I want to send this over the channel with no error, right? So this is my medium is my channel. But I know that my medium has a lot of distortions, right? So what Shannon said is, look, there is a fundamental property. There is something called as a capacity. If you are operating at a data rate less than the capacity, you can do reliable communications. You will have to invest in more and more resources, but by putting in enough resources, you will be able to get an error as small as you wish. Okay. On the other hand, if you are beyond the capacity, there is no hope. Okay, there is no scheme which will let you do that. And these limits actually have been used by engineers for a variety of reasons. They have actually driven modem design for the last 50 years. So people who are working with modem design, at the end of their design, they'll say, okay, to get an error rate of 10 power minus 5, how much power do I need? They compute that for their design. Then they go and say, let's see what Shannon tells me. And they'll say, oh, I'm very close to Shannon. I'm within 10%, so I'm good. Okay. So it's been an interesting journey. Now we can actually apply these concepts to our wireless channel. Okay. So you have this wireless medium, and there are statistical models for that. And given that, Shannon's theory will actually tell you what the capacity is. Okay. And by the way, even though we are not there, we are not too far away from capacity as well. So looking at how capacity behaves is actually a useful way of thinking about these systems. And what it turns out is that if you actually have n antennas at the transmitter and n antennas at the receiver, and provided they are placed sufficiently far, you are going to get capacity that is n-fold. The capacity also depends on other factors. So some of you may remember the log function. For those of you who don't know a log function, it's really a function with diminishing returns. Okay, just think of it as something. If you put more and more money, you're still going to keep on getting more output, but the output is going to keep on decreasing, right? So it's one of those sort of functions. And this is something that is called as the signal to noise ratio, right? So it depends on how much power you're sending. So the naive idea that we have, right? If I want to send at a higher rate, I think maybe I should pump in more power, right? And that should solve the problem. What this tells you, look, there is a logarithm in front of it. So there are diminishing returns, okay? So if you put more and more power, it's not like you're going to get more and more return. So on the other hand, in terms of the number of antenna, there is a linear scaling. So that's a good thing, right? The idea is that I should now put in more antennas, and that will be able to, that way I'll be able to pack more information in the same spectrum that's allotted to me. Okay. So this is the main reason why 4G has multiple antennas. So as I said, even third generation had multiple antennas, but it was primarily used to reduce the effective fluctuations in your signal. In 4G, what they're doing is primarily used for this, that you want to pack in more information within the same spectrum that you have. And it's really this linear scaling which gives you that. Okay. So because I don't have time, I'm not going to talk about what is called as smart antennas, but what I did was I've just scratched the surface. Okay. I mean, there are few important things that I felt that which are really contributing to this changes from 2G to 3G to 4G. So I've just tried to outline those technologies. But if you get into the details, right, there are a lot more interesting things. So I told you about this fundamental limits of Shannon, right? How do you approach those? Well, to approach those, you need error correcting codes, because whatever you do, you send some bits. What you get at the output is going to be a corrupted version. So if you want to recover the photograph that you sent exactly as is, there has to be a mechanism by which you should be able to correct the errors. Okay. So there are error correcting codes, and you can judge them against the limits that Shannon has told you. And there is enormous interesting activity, and one of the things which actually made data transmission possible in third generation was actually what is called as turbo codes. So these were codes invented in the mid-90s, and they operate very close to the limit that Shannon set. So they're actually, so every time you're using your cell phone for data, your 3G phone, it's actually using these turbo codes. Then there are these LDPC codes. All these recent Wi-Fi routers are actually going to be using these. Then there are these motions like space-time codes. So there is a lot of interesting error correcting codes actually built into your phone. As I told you, the number of antennas, but of course the other fact is that the amount of spectrum being allocated is also increasing. So that's another way. So not only are you packing more bits in the same amount of spectrum, but you're also increasing the total amount of spectrum, and that's another way you're getting to that. Now, there is, of course, I told you about these tiles, right? OFDMA has these space-time tiles, but how do you allocate these resources? Maybe you can apply a lot of smartness there, and there are a lot of people working on these things, okay? So there is a lot of smart scheduling that goes in. The more important thing that's probably going to differentiate, if 4G ever actually does penetrate into the market, one of the things it's going to bring is a very different topology. So 2G, 3G, essentially you have base stations communicating mobiles. But what 4G is going to do is there are going to be these special stations called relays. So you might be inside a building and you don't get good coverage, right? You can install what is called as a relay or a femto cell, okay, a femto base station. So it's not going to be as expensive and sophisticated as your base station, but it's going to be substantially cheaper, and you can put it in your premises, and it's going to give you better coverage. Okay, so the topology of your network itself is going to start changing, and there are different ways that operators are thinking how to use these things to improve your coverage. And lastly, I mean, base stations, they already talk to each other. Every time you're moving from one cell to another, you're handed over from one base station to another so that your call doesn't drop, right? So there is always already coordination, but in the future what's going to happen is it's going to go one step further. These base stations, it might occur that at the same time you're talking to both the stations, okay? So there is going to be more smartness and more coordination. So maybe I should stop at this point and